Hello, this is the next lecture. I believe it's lecture number 7, not that we're counting, from the cost-benefit analysis portion of the Army Cost Management Certificate course, technically titled MN4354, Financial Analysis and Cost Management. And the topic of this lecture is dealing with uncertainty in cost-benefit analysis. The last asynchronous lecture that you downloaded was dealing with time, inflation, and discounting. This is a similar sort of presentation, but it deals with uncertainty, when future events are uncertain, and how you deal with those in cost-benefit analysis. And I will tell you up front that this can be a bit complex, particularly the latter part of this presentation. But with that said, let's motivate it with something, a bit of a thought that's not quite so quantitative or so complex. So consider this quote by Dick Cheney after the 9/11 attacks. This was what he considered the 1% doctrine. It says, quote, "We have to deal with this new type of threat in a way we haven't yet defined. With a low probability, high impact event like this, if there's a 1% chance that Pakistani scientists are helping Al-Qaeda build or develop a nuclear weapon, we have to treat it as a certainty in terms of our response." What do you think? Does this make sense? As I said on my header here, according to the 1% doctrine, we don't need cost-benefit analysis. We don't need to decide whether it's worth it to do it. If there is any chance, a 1% chance, that it's possible, no matter the costs, we have to treat it as if it's absolutely certain. And what do you think about that? Does that make sense? And I offered you a reading called A False Sense of Insecurity by John Mueller, which takes a cost-benefit analysis approach to counterterrorism or steps to prevent terrorist attacks. And he certainly had a very different perspective from the 1% doctrine. And so here are some quotes from that reading. "Determining how to respond to the terrorist challenge has become a major public policy issue in the United States over the last 3 years. It has been discussed endlessly, many lives have been changed, a couple of wars have been waged, and huge sums of money have been spent, often after little contemplation, to deal with the problem. Throughout all this, there is a perspective on terrorism that has been very substantially ignored. It can be summarized somewhat crudely as follows. 1. Assessed in broad but reasonable context, terrorism generally does not do much damage. 2. The costs of terrorism very often are the result of hasty, ill-considered, and overwrought reactions." You can certainly read the reading to see what he goes into more detail on those two sort of summary points. But he concludes eventually that quote, "A sensible policy approach to the problem might be to stress that any damage terrorists are able to accomplish likely can be absorbed, however grimly. While judicious protective and policing measures are sensible, extensive fear and anxiety over what may at base prove to be a rather limited problem are misplaced, unjustified, and counterproductive." Accordingly, 3 key issues require careful discussion but do not seem ever to get it. 1. How much should we be willing to pay for a small reduction in probabilities that are already extremely low? 2. How much should we be willing to pay for actions that are primarily reassuring but do little to change the actual risk? And 3. How can other public measures which provide much broader benefits than those against terrorism get the attention they deserve? If terrorists force us to redirect resources away from sensible programs and future growth in order to pursue unachievable but politically popular levels of domestic security, then they have won an important victory that mortgages our future. For instance, measures that delay airline passengers by half an hour could cost the economy $15 billion a year. So, who was right? And I've created a discussion forum on Sakai that I encourage you to participate in. Remember, 10% of your grade is sort of your participation in these discussion forums. And what do you think? Does he have a good point? Where is he right? Where is Cheney right? How do we measure these things? How would we do a cost-benefit analysis of the things we do to try to prevent terrorist attacks? And ultimately, it comes down a lot to uncertainty. right? This is something that is, the probability might be very low. We don't know exactly, but the probability might be very low, but the impact might be very high. And how do you deal with those sorts of events where there's a lot of uncertainty, but it's not low likelihood, low impact, it's low likelihood, big impact. How do you compare that to things that are more certain? How do you handle generally uncertainty in cost-benefit analysis? And so that's what we're going to be talking about today. So when dealing with uncertainty in cost-benefit analysis, I sort of have these 5 topics that I want to cover. The ubiquity of uncertainty, expected value, probability distributions, risk aversion, and then certainty equivalence. Now the last 2 concepts are, to some degree, all the concepts are mathematical, a little complicated, but the last 2 are probably the most complicated, most mathematical. And I may have to break this up into 2 portions to keep the video size relatively small. And if I do that, I will cover these first 3 bullets in one, and I'll hold off on risk aversion and certainty equivalence, and I'll upload that as a separate video file. Although the slides are all going to be there on Sakai in one file. So the first topic in terms of dealing with uncertainty in cost-benefit analysis is the ubiquity of uncertainty. The reality is that there's always going to be uncertainty. It's almost an unavoidable factor in almost any cost-benefit analysis, right? Uncertainty can enter the cost-benefit analysis in many areas. In your assumptions, you've got to make, as we talked in the very first week, one of the steps is to make certain assumptions, and whether those assumptions are correct or not, there is uncertainty about that. And there's a reason they're called assumptions, right? If they weren't assumptions, they'd be facts. So there's uncertainty about whether that's the right assumption or not. Estimates of costs and benefits there's often uncertainty, particularly when you're looking at things in the future, right? But we saw just previously how sometimes we've estimated costs. There was this overconfidence in government that tended to underestimate costs, and in fact the costs ended up being much worse, much higher than anticipated. And so there's always this uncertainty about costs and benefits. And project outcomes, will it work? Will a research project produce a viable weapon system? Right? If you only invest in those weapon systems that are going to work, then you're not investing in anything new. You're not being very cutting edge. You're investing in old, proven technologies. Will a training approach achieve performance standards? Ex ante, you might believe that it does, but until you've actually done it, you won't know. Will a reenlistment bonus achieve retention goals? Right? Again, you can use all sorts of analysis to reduce the uncertainty, to have some expectation whether and it will achieve those goals, but there's inherently going to be uncertainty about the outcome of the project. Right? And so we have to know how to incorporate such uncertainty into cost-benefit analysis. So let me give you an example of the presence of uncertainty in cost-benefit analysis. So this is actually an actual cost-benefit analysis study in terms of electricity generation. And one thing was they were looking at 4 different types of electricity generation: onshore wind power, nuclear power, coal-fired power, and gas-fired. Right? And all of them, to some degree, because they use fuel and use oil, the costs of doing them depended upon prevailing oil prices. Right? And so onshore wind would be, and I don't remember the units were here, but 82 if oil prices were high, 64 if they were low. Nuclear was 80-38, coal-fired 83 versus 40, 87 versus 37. Certainly the last 3 options, had a dramatic difference in their costs depending upon whether oil prices were high or low. Well, at the time of the study, this was back in 2012, here's what U.S. crude oil prices looked like in 2012. Up and down, from a high of over $100 a barrel to a low of under $20 a barrel. Well, this is in 2012 dollars. This is leading up to 2012. But these are all inflation adjusted. Right? These are the real costs. And so when you see this fluctuation in oil prices, and you're projecting out a project over many years, you're going to have inherent uncertainty in terms of what your costs are going to be. So for any course of action, the cost of benefits could be highly uncertain. And this is especially true when they're driven by other uncertain values, like in this case, when your costs are driven by oil prices, which themselves are uncertain. Now, one of the key notions here is, in terms of dealing with uncertainty, is expected value. To motivate expected value, consider the following. In cost-benefit analysis, it is often the case that the actual value of some parameter is uncertain, right? Whether it's something we assumed, whether it's the actual cost, whether it's the time something will take, whether it's the success rate. There's some parameter which is uncertain. But we know something about the possible values. Maybe it's a range of values, but we know something about the possible values of the parameter and the probability of each possible value, at least an estimate. Well, when you have those things, in those cases, you are able to, and it is helpful to, calculate the expected value of the uncertain parameter. What do we mean by expected value? Well, the expected value is the sum of each possible outcome weighted by its probability of occurrence. In other words, it's the weighted average of the values of the uncertain parameter. Take all the possible values and do a weighted average, with those weights being the probabilities. Now let's motivate this. So here, just repeating what the last two bullets here. It's the sum of each possible outcome weighted by its probability of occurrence, or the weighted average of values of an uncertain parameter. So suppose that there are n possible values or outcomes, right? We'll talk about examples where you roll a die, where there's 6 possible outcomes of rolling a die, or you spin a wheel, or there's so many possible outcomes. And suppose the possible outcomes and the values associated with each outcome are V1, V2, V3 up to Vn, where n is the number of possible values or outcomes. And suppose that those occur with respective probabilities P1 through Pn. Right? P1 is the probability that the parameter has value 1, P2 is the probability that it has value 2, and so on. Then the expected value of this parameter is given by expected value equals V1 times P1, the first value times the probability of the first value, plus V2 times P2, the second possible value times the probability that we see that value, plus V3 times P3, plus so on and so forth, until we get Vn times Pn. So we do value times probability of that value summed across all possible outcomes. To better illustrate this and not make it so mathematical, let's play some games. Okay? The first game is going to be deal or no deal. So we're going to play some game shows here. So deal or no deal, I must confess I've never watched a full episode, but I think most people are familiar with it. It's the I want to say Harvey Keitel, but no, I'm blanking. No, not Harvey Keitel. However, the guy who does the America's Got Talent. It'll come to me in a second. Howie Mandel. Harvey Keitel, Howie Mandel. It's pretty close. I'm forgiven. So this is the Howie Mandel show, or at least for a while it was, where there were different suitcases that had different values in them, and you would choose to eliminate suitcases, and hopefully you would get the suitcase with the most money in it. But at various points, you're offered an out. Like the banker will say, hey, you can quit now and I'll give you this, or you can keep going and play the gamble. Well, suppose there are 3 suitcases left. So the way the game works is certain suitcases are opened and taken off the table. So now you know there's 3 suitcases left. One contains $200, one contains $1,000, and one contains the grand prize of $300,000. Right? What is the expected value of continuing to play, of this game at this point? Well, you're equally likely to end up with any one of those 3 at this point. So remember, our formula for expected value is, V1 times P1 plus V2 times P2 plus V3 times P3, all the way out to Vn times Pn, where n is the total number of possibilities. So you sum value times probability for all possibilities. Well, in this case, there are only 3 possible values. You end up with the suitcase with 200, suitcase with 1,000, suitcase with 300,000, right? There is a 1/3 chance of each, right? So your expected value is going to be 200 times 1/3, plus 1,000 times 1/3, plus 300,000 times 1/3, which comes out to $100,000, $100,000, and $400. So that's the expected value, right? So in other words, if you were in this position again and again, and you played it, you could, play it once, rewind time, play it again, do it again, do it again, do it again, assuming you didn't take the knowledge back with you which suitcase was the ideal suitcase. And if you averaged your earnings over all that, on average, you would earn $100,000, $100,400. Therefore, as the way this game works, the banker will periodically offer you, a certain amount of money, and you can either accept it and be done, or keep trying to open the suitcases and hope for the grand prize. So if the banker, in this case, offered you $100,000, you should reject it and take your chances, right? Because your expected value is $100,400. So $100,000, that's not as much as I can get or expect to get on average by continuing. So you should reject that offer. Or should you? More on this later, right? In fact, as we'll see, most people would, and I would say should, accept the offer of $100,000 even though it's below the expected value. And we'll talk about that when we talk about risk aversion. All right, well, what about another game show? Deal or No Deal? Here's a game show I watched a little bit more of, being a trivia buff. Who Wants to Be a Millionaire? So here's a true scenario faced by a contestant on the game show Who Wants to Be a Millionaire several years ago. He was at the $125,000 question with no lifelines remaining, right? And if you guys know what those are, and was given the following question. What Philadelphia Eagles head coach has the most victories in franchise history? A. Earl Greasy Neal, B. Buddy Ryan, C. Dick Vermeil, or D. Andy Reid? The problem was he had no clue. He had absolutely no clue and would have to guess randomly in order to answer the question. And the question, facing him is, should he guess? Should he in fact guess? He's got 4 possible answers, a 1 in 4 chance of being right. If he chooses the right answer, he would get the $125,000. But if he chooses the wrong answer, he would fall back to $32,000 and he would be done and walk away with $32,000. But his third option was to walk away without even answering the question with $64,000. What should he do? Right? Should he guess or should he walk away? Well, we have this handy-dandy, sort of tool of expected value. So we ask this question, what is the expected value of guessing? Well, the analysis, first of all, expected value is about values and probabilities. Well, so let's think about probabilities. What is the probability of guessing correctly? Well, if he really is random and he has no idea, he's a 1 in 4 chance of guessing correctly. What is the probability of guessing incorrectly? Well, he's a 3 in 4 chance of guessing incorrectly. So what is the expected value, therefore, of guessing? Well, expected value is 125,000. That's the one value that he could get. Times the probability of that value. That's where if he guesses correctly, he gets 125,000. So that's 1 times 1/4. Plus 32,000 times 3/4. So the expected value of guessing is 55,250. Again, each possible value multiplied by its probability and summed up across all of them. And that's how you get the expected value. So the expected value of guessing was 55,250, which is less than 64,000. Right? He could walk away with 64,000. So the decision in that case would suggest to walk away. Right? By the way, there is something for those of you who know the game. It is ignoring something we call option value, right? Which is, I've sort of assumed that you answer the question correctly, you get 125,000, and that's the end of your day. In fact, if you answer that correctly, you then are asked another question, and you have potential for even more earnings. So there's what we would call option value. But for our purposes, let's assume that he's not expecting to go beyond that point. So it's either 125,000 if he answers right, 32,000 if he answers wrong, and 64,000 if he doesn't even try to answer at all and walks away. And if that's the case, then, and he really has no idea what the right answer is, he should in fact walk away. But I lied. That's not actually what happened. He actually had a 50-50 lifeline left. So he had one lifeline left when he faced this problem. And this lifeline, the 50-50 lifeline, is one that basically eliminates 2 of your 4 answers, so you have a 50-50 chance. And so 2 of his choices would vanish. And so the choices that were left to him after he played his 50-50 lifeline were A, Greasy Neal, or D, Andy Reid. So now, he still had no idea. But should he guess between these 2? Well, the expected value of guessing, right? He's got a 50% chance of getting the right answer. If he gets the right answer, he gets 125,000. Wrong answer, he walks away with 32,000. So the expected value of guessing now is 125,000 times 1/2 plus 32,000 times 1/2, or 78,500. That is now greater than 64,000. So that is greater than the walkaway value, right? And significantly, fairly significantly so. Right? If you were highly risk averse, you might still walk away. But even if you were a little bit risk averse, this suggests that you're better off guessing. So what happened? He did. He gave it a shot. He guessed, and he guessed right. And for you sports fans out there, the correct answer then was Greasy Neal. At the time of this game show, Greasy Neal had the most wins as a Philadelphia Eagles head coach. However, within a couple years of that, Andy Reid actually later passed Neal. So Andy Reid became the winningest coach in Philadelphia Eagles history. But at the time of the game show, the right answer was Greasy Neal. So there's sort of applications of expected value both in the deal or no deal scenario as well as in the Who Wants to Be a Millionaire scenario. Let's consider an even simpler game, not a game show, but just rolling dice. So suppose we have a game where a player rolls 2 dice, 2 6-sided dice, right? So if you have 2 6-sided dice, each die has 6 possible outcomes. So therefore, there are 6 times 6 or 36 possible outcomes, right? You could have a 1 on one and a 5 on the other, a 2 on one and a 3 on the other. If there's 6 possible outcomes in one die roll, 6 in the other, combined, there are 36 possible outcomes in terms of the different combinations. Not necessarily 36 different values, right? But 36 possible outcomes. And the rules of the game are that the player receives $5 if the 2 dice show the same number. Roll 2 1s, 2 2s, 2 3s, etc. Then the player will receive $5. However, he has to pay $1 if the numbers in the dice are different. So you receive 5 if they're the same. You lose 1 if the numbers on the dice are different. What are the probabilities here? So we try to figure out whether this is a game I might want to play or not. What's the value of this game? Well, first, again, what are the probabilities? Well, what's the probability of winning $5? Well, it's that how often you win $5 if the 2 dice show the same number? Well, they could either be both have 1s, both have 2s, both have 3s, both have 4s, both have 5s, both have 6. So of the 36 possible outcomes, 6 of them are with both numbers being the same, and so of those 6, those are the 6 outcomes in which the player would win $5. So there's a 6 out of 36 or a 1/6 chance of winning $5. What about the probability of having to pay $1 out? Well, all the rest, right? The 30 other outcomes out of 36 are you are not rolling the same number. You're rolling 2 different numbers. So that's 30 out of 36 or 5/6 chance that you're going to have to pay $1. So what's the expected value of this game? Well, the expected value, remember that there's only 2 possible values here. So it's you either win $5 or pay $1. So there's value 1 times probability 1 plus value 2 times probability 2, right? That's your expected value when you only have 2 possible values. Well, the first one, value 1, the winning value, is a 1/6 chance. The losing has a 5/6 chance. Of course, the winning value is $5. The losing value is negative $1, right? So the expected value is going to be $5 times 1/6 plus negative $1 times 5/6, right? Or $5 times 1/6 minus $1 times 5/6. That comes out to 5/6 minus 5/6 or $0. So because the expected value is 0, we call this a fair game, right? That if you had to pay $1 to play this game, you wouldn't want to do it. But if somebody paid you $1 to play this game, you would want to do it, right? In fact, if they paid you a penny, right, you're sort of indifferent because your expected value is 0. But it's a fair game, unlike some of the games we'll talk about in a second, where the house always wins. In this game, if you did it over and over and over again, you would lose some money here, gain some money here, but in the long run, you'd be expected to end up exactly where you started. Now, so those examples allow us to give you some interpretation of what expected value means. First, expected value, and this is something that's important, that people sometimes get confused, is not the value of the uncertain parameter that you expect to actually observe. It's not what you expect. I expect to roll, 2 2s, or I expect to roll. It's not, what you expect to happen. In fact, it may not even be a possible value of the parameter. For example, in the deal or no deal game, the expected value of staying in the game was $100,400. But the only possible values were either that you got the suitcase with $200, the suitcase with $100, or the suitcase with $300,000, right? So the expected value wasn't even a possible value. But when you take all the possible values, weight them by the probability, that's what you get. In the Who Wants to Be a Millionaire example, right, the expected value was $55,250 when we had 4 choices to choose from, or it was $78,500 when we had only the 2 outcomes to choose from. But the possible values are either you guess it right and get 125,000, or you guess it wrong and get 32,000, right? So the expected value is often, generally, is not one of the possible values. It's usually not one of the possible values because you're doing weighted average of the possible values. Similarly, the roll of the dice game, right? The expected value is 0. But the possible values were either $5 or -1, right? You either receive 5 or you pay 1. There would never be a case when you roll the die and would pay nothing. You would either pay $1 or you'd receive $5. But still, the expected value was 0. You know, you sort of think about expected value as a sort of a long-run average, right? If you were to repeat the scenario many times and observe the uncertain parameter each time, whether it's your earnings, the roll of the dice, what you get in each of those game shows, the average of the observed parameter values would get closer to the expected value as you observe more and more values. Right? The idea that we might not. If you think about it, for example, suppose there are, echoing back to the discussion from earlier this week, actually today, since I'm recording this on Tuesday, the hospital. Suppose a hospital has 3 babies born each day, and they're equally likely to be boys or girls. Well, the expected value of boys and girls in any given day is 1.5. But you're not going to get 1.5 boys. You're going to either get no boys, 1 boy, 2 boys, or 3 boys, right? But the expected value, it would be, 1.5. Now, I think, if I'm doing my math correctly, right? So what would happen over time is you would certainly never observe 1.5, but the average over time would average out to 1.5. 0 one day, 3 the next, 2 one day, 1 the next, and over time the average number of boys born per day, if there were 3 born each day, 3 babies total born each day, would be 1.5. So adding on expected value, one thing when we have more complicated variables is we've got to introduce these notions of probability distributions. So suppose a fair coin is tossed 3 times. Right? This is very similar to the boys and girls, 3 babies being born, are they boys or girls? And suppose we toss a coin 3 times, and we're looking at heads and tails, and let the variable x be the number of heads. What is the expected value of x? The expected number of heads when you toss a coin 3 times. Well, it helps to define the probability distribution of x. What do we mean by probability distribution? Well, a probability distribution is the probability values that are assigned to each possible outcome of an event. And the probability values must sum to 1, or 100%. Right? I mean, there's, if there's a 10% chance of this, a 20% chance of this, a 30% chance of this, those better sum up to 1 and no more than 1, right? You can't have, well, there's a 60% chance of rain and a 70% chance of no rain. Well, that's not possible, right? And so they have to be able to sum up to 1. So probability distribution is basically all the different probabilities associated with all the different possible outcomes of an event. So in this example, when we're tossing a fair coin 3 times, right, there are 8 possible outcomes of 3 coin tosses. You could get heads, 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 tails, heads, tails, heads, tails, head, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, or tails, tails, tails. Those are the 8 possible outcomes. Right? And so remember, if x is the variable is the number of heads, right, then the possible values of x, we could have no heads at all. It's all tails, the very last outcome listed above. We could have 1 head. We could have 2 heads out of the 3. Or we could have all 3 of them be heads, which is the first outcome above. So what that means, if we think about this, that can help us determine the probabilities. So if we look at what's the probability that we have 0 heads? Well, there's only, out of these 8 possible outcomes, only 1 of them, the very last one, has 0 heads. So 1 out of the 8 outcomes has 0 heads. The probability of 0 heads is 1 out of 8. What about having 1 head? Well, let's see. This outcome here, heads, tails, 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 heads, tails, 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 heads. So there's 3 outcomes in which you observe 1 head. So there's 3 out of 8 is the probability of having 1 head. What about for 2 heads? Well, heads, heads, tails, heads, tails, heads, tails, heads, heads. Again, there's 3 outcomes in which there are 3 heads. So there's 3 out of 8 is the probability of observing 2 heads. And finally, what's the probability of observing 3 heads? Well, there's only one outcome, the first one, where they're all heads, out of the 8, in which you observe 3 heads. So there's the probability of observing 3 heads is 1/8. And we're lucky, notice they do sum to 1. 1/8 plus 3/8 plus 3/8 plus 1/8 is 8/8. Sorry, I still have that loose tooth, which makes me lisp. That's hard to say. 8/8. So therefore, they do sum to 1. So that gives a probability distribution like this. For each possible value of x, x can be 0, 1, 2, or 3. The probability of x is 1/8, 3/8, 3/8, 1/8. And that's one way we represent a probability distribution for an uncertain parameter. Then that helps us to then calculate the expected value. So the expected value, remember, it's each possible value times its probability plus, summed across all possible values. So it would be 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8, right? So the expected value is 1.5. Just like I said about the number of, if these were boys or girls being born, the expected value, number of boys or girls being born, if they're equally likely, is 1.5. So again, but notice this is something you'll never actually observe. If you flip a coin 3 times, you'll never actually observe 1.5 heads, but the expected value is 1.5. Now consider the idea of the state lottery. Right? And we'll talk about expected value in terms of the state lottery. So state lottery, suppose state lottery follows the following rules: that you can choose 3 digits from 0 through 9, right? And repeats are allowed. So what that means is your first digit can be anything from 0 through 9. So there's 10 numbers there, right? Not just 9. There's 10 possibilities for your first digit. There's 10 possibilities for your second digit. There's 10 possibilities for your third digit. And you could repeat yourself. So you could be 999 or 000 or 00. You could start with 001, whatever. That means there are 1,000 possible choices. 10 times 10 options in the first digit, 10 for the second, 10 for the third. So 10 times 10 times 10, or 1,000 possible choices. And let X be your winnings from the lottery. And X is $500 if you choose the correct number. So if you choose the correct number, 1 in 1,000 chance of choosing the correct number, you win $500. Otherwise, you win nothing. Okay, so the probability distribution is X, your winnings can be either 0 or 500. And the probability you win 500 is 1 in 1,000, or 0.001, or 0.1%, if you want to put it that way. And the probability you win 0 is 0.999, right? Every other possibility. 99.9% of the time, you will win nothing. Right? All right, so what's the expected value then? Well, it's again multiplying the weighted average of all the possible values weighted by the probability. There's only 2 possible values here. You win nothing or you win $500. So it's the first value is $0 times a 0.999% chance of that, right? Plus $500 times a 0.001% chance of that, or 0.001 chance of that, or a 0.1% chance of that. Well, of course, 0 times anything is 0, but 500 times 0.01 is 50 cents. So the expected value, of the lottery ticket in this example is 50 cents. On average, each ticket wins 50 cents. And that's something, of course, that's very important for the state to know, because they want to know what they should sell it for and what their profit will be. Well, if they sell tickets for $1 each and the expected profit is 50 cents each, then if they sell tickets for $1 each and the expected earnings or winnings are 50 cents each, that leaves them, as a state, expected profit of 50 cents each. Of course, they have to account for costs, etc. But these are sort of the calculations of expected value, which will dictate how much they can and should charge for lottery tickets. Note again, though, the expected value is not necessarily a possible value of the uncertain parameter. Right? In this example, the expected value is 50 cents. But the only possible values of X are either 0 or 500. Right? So again, don't confuse with expected value with the value you expect to actually observe. All right, well, let's get a little more interesting. Let's go to Vegas. Let's look at expected value applied to the roulette wheel. Well, the roulette wheel has alternating black and red slots, right, numbered 1 to 36. But it also has 2 green slots numbered 0 and 00. Right? And there are many different ways you could bet. But certainly if you could bet on, as you see here on the right, you could bet in the first 12, the second 12, whatever, odds, evens. But let's just take the bets on betting on a single number. If you bet on any one of the 38 numbers, again, the 1 to 36 numbered slots plus the 2 green 0 slots, if you place your money or your bet on any one of the 38 numbers, if you win, it pays odds of 35 to 1. So if you bet $1 on the winning number, you receive $36, so your net winnings are 35. Right? So should we play roulette? What are the expected value here? Well, let X be the net winnings from $1 bet on a single number. Well, the probability distribution is that you will lose that dollar, or you will have a net return of $35. Right? You'll get 36 back, but you don't get your bet of $1 back. So you can either win 35 or lose $1. Well, you win 35 1 out of every 38 times. Right? It comes up on your number 1 out of 38. Every other time, 37 out of 38 times, you lose your dollar. Right? And so that's the probability distribution of betting on a single number on the roulette wheel. So what's the expected value? Well, there's only 2 possible values, -1 or 35. So we multiply them each by the associated probability. So it's -1 times 37 over 38 plus 35 times 1 over 38. And it comes out to 0.05, negative 0.05, or a negative nickel. Right? What that means is, on average, the house wins 5 cents on every bet. Of course, they never actually win 5 cents on a bet. They either pay out $35 or they get $1, right? In this case, or if you bet $10, but the idea is that the house wins on average. You can play the roulette over and over again, and a fair game would have, of course, expected value of 0. But this is not a fair game. This is a game in which the house wins, right? That's why they're in business, right? And the wheels are spinning 24/7, winning big money for the house. Right? Roulette, for me, I like to gamble. I don't mind gambling, going to the casinos, but boy, roulette just seems to me to be a tax on the stupid. And some people get into it. It can be fun. If it's worth the fun, you get the free drinks, that's fine. But I'm someone who, just knowing the odds, I say, let me apply a little bit of what I know. I'm not a great blackjack player, but I know a little bit about certain rules that can have me retain my money for a while, and maybe if I can count cards enough, and I can make some money. But anyway, but roulette wheels are something that are consistent money earner for the casinos. All right, so that brings us to the topic of risk aversion. As I said, we're going to take a break. I got to make sure, first of all, this recording even worked. Lo and behold, I'm sure I'll probably find out that this didn't actually record my voice or something. We'll see. And then I will record a separate video of the last 2 topics, risk aversion and certainty equivalence. So thank you very much, and stay tuned for part 2.